All right. Hello, everybody. Thank you for tuning in to Lecture 20, going through Section 2.5 of Vakil. Um, you'll notice that my camera is off today. This is because I have the super flu. Yes, it's the day after Christmas. Yes, I spent all of Christmas locked away in my room. That's why there hasn't been a video for 2 days, is because I've been sleeping. So, with that said, we're hoping to kind of have not lost a lot of momentum. We're hoping to get through um, 5 pages basically today. Um, if we don't, it's not the end of the world, but it'd be nice to finish it off today. So, this section is called Recovering Sheaves from a Sheaf on a Base. And to really kind of understand what this means, we need to know what the base of a topology is. And so the intro that Vakil gives is that sheaves are natural things to want to think about, but hard to get our hands on. We like the identity and gluability axioms, but they make proving things trickier than for pre-sheaves. We have discussed how we can understand sheaves using stalks and compatible germs, but we'll now introduce a second way of getting hold of sheaves by introducing the notion of a sheaf on a base. Warning, this way of understanding an entire sheaf from limited information is confusing. You may find it helpful to focus on the central insight that this partial information suffices to determine the germs and that they are compatible with nearby germs. And so then he starts off with the definition of a base of a topology. Let X be a top space. Then the base of X is a subcollection of open sets BI is contained in UJ, which is open in X, such that each UI is equal to a union of BJ for some index. Of J. So one example that we've seen early in your mathematical life. So if X is Rn, then the way the classical topology is defined is with open balls. And open balls form a classic base of the standard topology. And Garrett, since you haven't taken analysis, this one actually does not apply to you. So let me clarify that if we have a point B naught and a distance epsilon, then open sets in R in the standard topology look like unions of these open balls.
Okay.
And that it is sufficient to basically start with just the open balls, because say you have some weird open set. Well, it's just a union of these open balls. In a similar way, you can construct, like in Rn, weird shapes that are like you would think, okay, well, maybe if we extended this into R2. Oh, I can just do it here. Hold on. If we extended this into R2 and maybe did, there's not really a convenient spot for it. R cross R, and maybe we had like this here, and then this here. Well, this makes kind of an interesting shape in what's known as the product topology. Because it kind of looks like boxes, right? So if this is starting point, this is the starting point, this is the top height, this is the top height. It suffices that the product of these two open sets looks like this section, and then furthermore that the product of this other open set looks like this. And so this is kind of a classical real analysis thing, is the product of well, the product topology is nice because it's a generalization of the product that we've seen categorically. So it just means that things factor through the product to get to their individual things, and so on each axis you retain the original topology. You just store it in terms of Cartesian products. Oh, yeah, did I record? Yeah, I'm recording. Okay. Am I?
You are.
Okay, cool. I am. Uh, so as an application of how we use such bases to check the continuity of some map, you need only think about the pullback on balls on Rn as part of the traditional delta epsilon definition of continuity. So like if you have pi from a topological space X to Rn, then to generalize topological continuity, you just look at pi inverse of open balls. And so like it gives you a way to check continuity easily.
Okay.
So now let F be a sheaf on a topological space X with a base BI, or we'll just go with beta I, that's fine. Then consider the information, which is the set of sections on these beta i's paired with the restriction maps of intersections. Which is a subset of the information contained in the sheaf. We are paying attention only to the information involving elements of the base, not all open sets. We can recover the entire sheaf from this information. This is because we can determine the stalks from this information and determine whether and when the germs are compatible. So basically, we have a subcollection of open sets, and we have all of the information about the restriction maps to each other, meaning we have intersections, and so we can build out any missing information of open sets that we don't have already, using kind of the laws of a topology. This suggests a notion called a sheaf on a base. A sheaf of sets. I guess I'll write this in yellow. Definition. A sheaf of sets on a base BI has that, and I'm just going to break this into a bunch of parts. So for every BI in the base, there exists a set F of BI, which is notably not a section. Maybe they just used the wrong F. Normally we reserve that for functor, but okay. And then if BI is contained in BJ, there exists a map res BJ to BI from F of BJ to F of BI with res BI equal to ID on F of BI. If BI is contained in BJ is contained in BK, then res BK to BI is equal to res BJ BI composed with res BK BJ. This is all a pre-sheaf on a base. And then, of course, to complete the rest of it, we have the base identity axiom, which is our analog of the actual identity axiom, that if B is equal to the union of BI, and we have Fi in the base section on BI, such that for all I, Fi equals Fj on any U open in BI intersect BJ. Or we'll call this BK actually, because that's the notation they end up using. Oh my god, I started reading off the wrong definition. Well, this does show up later, so I'm just going to move it all down. And I need to charge my Apple Pencil.
Death, taxes, and Tim charging his Apple Pencil.
Huh?
The three things guaranteed in life: death, taxes, and Tim having to charge his Apple Pencil.
And category theory. You can't forget category theory.
Forgot about category theory for a second. That
Yeah.
was a nice couple seconds right there.
I feel like I should pop my camera on to show the YouTube, the shirt.
I think you have to show the YouTube this shirt.
Yeah, so my dad is somewhere between an applied mathematician and an economist. And so he always gives me a hard time about the fact that I do so much category theory. But he got me this shirt for Christmas. Oh no. Hold on. There we go. He got me this shirt for Christmas that says, I find your lack of interest in category theory disturbing. So, anyway, yeah, fun times. Basically, the idea is that the same identity axiom basically holds. We just have an added condition about this stuff, about the base. And I'm pretty sure glueability works very similarly as well. Um, I'm just gonna take the chance to blow my nose. This flu is terrible. Okay, let's check in. Any day now. All right. Once it gets up to 25, I reckon we're good. Hopefully the Dayquil I took kicks in soon.
That'll help.
Yeah. All right, here we go. Okay, so moving this down, moving this over, this will be relevant later on in life. But if B is equal to the union of BI's, and if F and G are in the section over B, such that their restriction maps from B to BI, F is equal to the restriction map of B to BI of G, then F is equal to G. Um, and it's worth noting that there's a very big for all I in here. Um, that I feel like I keep forgetting to really highlight. Um, for all I. And then glueability, base glueability. Glue, I really wonder if I've been spelling that wrong this whole time. It would be kind of funny if I did. But if B is equal to the union of BI, and if F and G. Nope. Oh my gosh, I started reading the wrong one again. And if. And now the rest of this definition can carry over. And if Fi is in the section on Bi such that for all I actually it's for all K. So they agree on this intersection. Then there exists F in FB such that the restriction map from B to Bi of F is equal to Fi for all I. Yeah, and so this is very similar to our original gluing theorem. So functionally these act kind of the same way. It's just we're rebuilding these things into our original definitions with open
Yeah.
sets using stuff that is kind of familiar with like bases. It's also worth noting that if a base generates a topology, its like generating set is also open. So like that's kind of an easier way to think about it. This just gives us a wider range of generality. But as a theorem, let Bi be a base for X, and let F be a sheaf of sets on Bi. Then there exists a sheaf F extending F with isos from the sheaf on Bi to the base sheaf on Bi. Agreeing with restriction maps such that the sheaf is unique up to unique isomorphism. So it's a universal thing. Yeah. So to construct the sheaf F, we want it to be equal to the sheaf of compatible germs of F. And we can do this by letting the stalk of a pre-sheaf F on a base at P in X be FP is equal to the co-limit of F of BI, where the co-limit is over all BI, in the base containing B. with P and BI. Yeah. And so we're basically identifying all of the things that end up agreeing at some point into sections of like compatible things. And this is exactly the definition of a colimit, and it's also exactly what we want the stock of a presheaf to be. It's the collection of compatible germs, right, at P. And then, of course, F ends up being the collection of, like, then script F over U is equal to the set of FP. Wait, it's equal to the section. It's equal to the stocks in FP such that P is in U. Um, such that for all P in U, there exists B with P and B contained in U, and S in F over B with SQ equal to FQ for every Q in B, meaning compatible germs between B and U for each such B. So we're collecting all of the compatible germs across BIs. And then this is a sheaf for the same reasons that the sheaf of compatible germs was. Um, and then we just kind of want to show that there's an isomorphism between this sheaf and F of BI. But it's pretty natural from the way that we said that restriction maps work, right? Like we said all of our restriction maps agree. So then everything that is a pullback of a restriction map has to agree. And I think that that really just kind of formalizes it. And then surjectivity is clear because we're working on the same set, and we don't, if we have injectivity and we have something from a set to itself, then it has to be surjective as well. Similarly, if you have um, something that is a function that is surjective from a set to itself, it also has to be injective. It's called the big payoff theorem. So in that way, it's kind of nice. Um, and then that this is unique up to unique isomorphism. I think it's that we just kind of can't construct another sheaf that is different. Um, or that if we were, it would just be an automorphism of the same sheaf. So is all of this kind of good so far?
Yeah.
So this theorem shows that sheaves on X can be recovered from their restriction to a base. It is clear from this argument that if F is a sheaf or if script F is a sheaf and F is the corresponding sheaf on the base B, then for any P in X, the localization of script F at P is naturally isomorphic to the stock at P in the base. It's a statement about objects, and so we kind of want an analogous statement about morphisms. So just as another important morphism, or as a theorem, there we go. Words. Morphisms of sheaves correspond to morphisms of sheaves on a base. And Yeah. Basically, we get a commutative diagram. Um, I think we're about to have our first 3D diagram. So if we have this, I don't know if I want that angle. I need to draw a good square before I can do this. Okay. And so then if we have script f of bj, script f of bi, and one of these needs to move over. Script g bi, script g bj. Okay, there we go. Um, then basically this commutes. This commutes nicely. Um, and then phi 1, phi 2, phi 3, and phi 4 are isomorphisms.
Can you just
Alpha,
give me a second to get it down real quick?
yeah, alpha and alpha prime, beta and beta prime, gamma and gamma prime, and then theta and theta prime. So, basically, so phi I is a fully faithful functor. Um, for every one less than or equal to I less than or equal to 4. And then basically phi I guess. Phi 1 of,
Am I going up just 1 second?
yeah.
A little bit more. Thank you. That's theta right there. Um, okay, I think I have everything.
Okay. So then phi 1 of beta is equal to beta prime. as a functor, right? Um, but then phi 4 of beta is equal to beta prime inverse, and so on. Um, and so this, if we were to do this for everything, it would work. It's worth noting that beta and theta, beta is equal to the restriction map from f of bi to f of bj. And theta is the restriction map from g of bi to g of bj. And then beta prime is the script version of that. And we know that those work, right? We know that there is a natural isomorphism by construction to beta prime and theta prime. And so then it becomes an issue of showing that alpha prime and gamma prime work. Um, and I think the way that we do that is with compatible stalks. So these two come from construction. And then, what do we call them? Gamma and alpha. Alpha comma gamma to alpha prime, gamma prime comes from compatible stalks. So, um, yeah, so the above constructions and arguments describe an equivalence of categories between sheaves on X and sheaves on a given base of X. Um, and yeah, we have functors in each direction. Their compositions aren't the identity. It will be useful to extend these notions to OX modules. You'll readily be able to verify that there is a correspondence, really equivalence of categories, between OX modules and OX modules on a base. Rather than working out the details, you should just informally think through the main points. What is an OX module on a base? Given an OX module on a base, why is the corresponding sheaf naturally an OX module? Later, if you are forced at gunpoint to fill in details, you will be able to. Well, um, I mean, I guess that's a good question. So, I'm kind of curious about what a base of an OX module is meant to look like. Um, because I don't. I'm not sure. So if we have a ringed topological space that has structure sheaf OX, and we have a basis of the topology B, then the module on each basic open is a section on the open subsets of each open set in the base. And then restriction maps are module maps between open subsets. Yeah. Okay. Um, okay. So gluing sheaves is what's called the next section. Um, so theorem, let X be equal to the union of UIs be an open cover of X with sheaves Fi on UI with isomorphisms phi ij from Fi on UI intersect Uj isomorphic to Fj on Uj intersect UI. That agree on triple overlaps, i.e. phi jk, phi ij is equal to phi ik on ui intersect uj intersect uk. This is called the cocycle condition. And this is something that we've encountered in homological algebra. These sheaves can be glued together into a sheaf on X. These sheaves can be glued into a sheaf F on X with isomorphisms F restricted to UI go into the ith sheaf, and the isomorphisms over intersections of open subsets are the obvious ones. And so the thing is that we don't necessarily have a finite open cover, so we can't just like induct these things. So I don't know. How would we prove this? I mean, I guess it's just kind of take open sets. This seems like a kind of painful thing. Yeah. I don't know. I feel like this is just going to kind of be a pain to prove. Um, and I think I understand kind of the importance of it. I'm okay with skipping this proof and maybe just doing it later on my own time. How do you feel about it, Garrett?
We could do that.
Okay. Then in that case, let's take a 5-minute break until 8:30 and then we'll come back with section 2.6.
All right.
Sheaves of abelian groups. Abelian categories. Okay. Whenever you're back.
All right.
So, this is a pretty short section, and I'm not entirely sure how important it is for us. Um, we've kind of just been going through Vakil for the sake of going through Vakil. I don't have a strong sense of like, besides the fact that these constructions show up in research, I don't have a strong sense of like, oh yeah, we're gonna need like abelian category stuff. But yeah, I don't know.
Yeah, it's just good to have.
Yeah, yeah. I just mean that I don't know. I won't be too worried if I'm like missing a little bit of this.
Okay.
So the thrust of this section is that we can treat sheaves of abelian groups or OX modules like vector spaces or modules over a ring.
Mhm.
Um, and so that we can understand like kernels, co-kernels, exactness at the level of stalks, which are just abelian groups. Um, and so basically everything breaks down into abelian groups.
Yeah. Okay.
Um, and so yeah. The theorem, the stock that had two L's, the stock of the kernel is the kernel of the stock. Rather, the kernel of a map from F to a sheaf G stalked at P is isomorphic to the kernel at the stalk of P to the stalk at P. Um, and so to accurately describe this isomorphism, we want to look at, basically the stalk at P of the kernel, and then we want to figure out a mapping. So if we let phi be such a mapping, then the stalk at P is the collection of things which zero out um, through this morphism. And so it's collections of F, comma U, where basically F from A into F into G goes to 0 on U. And then this is going to get mapped to the kernel of the stalks, which is the collection of G and U, such that G from AP to FP to GP equals 0 in GP for every U. And so naturally there is a real equivalence here that it doesn't matter how we do this. And this is because kernels commute with colimits. Um, right, so we said that like localization generalizes stalks, well, colimits generalize localization, so colimits basically generalize stalks, and so stalks commute with kernels. Um, um, so is this kind of a clear construction?
Yes, it is.
Okay. Um, a little confused about this business of the co-kernel. Okay, so the way he sets this up is he says, let phi from F to G have Coker phi in category of pre-sheaves, called script H, pre. And then let its sheafification go to H. And what is this really equal to? Well, this is equal to the image of phi mod. No, it's equal to G mod the kernel of phi. No. Yes? It's equal to F mod kernel? Hold on. Am I dumb? God, I'm tired. Oh, that has nothing to do with the kernel. It's Gmod, the image of phi. There we go. Okay. I knew it was one of them. Oh, Lord, I'm tired.
Yep.
Um, so then the sheafification of this is the collection of all things that agree in the way that a sheaf does. So all of the things that have identity and gluability. Um, and then as a proposition, the composition G to H, which is G mod M phi. Well, I guess it's the sheafification of G mod M phi. Um, is equal to the co-kernel of phi in the category of sheaves.
What does the line above it mean?
Sheafification.
Oh, okay.
Normally it means closure, but
Mhm.
because this is in pre-sheaf, and so then when we sheafify it through sh, we get sheafification. So it's just all the things that satisfy identity and gluability. Um, and then basically the diagram for this that makes all of this work is the universal diagram. Uh, and don't worry, I'll add arrows. So basically, if um, this commutes, then we end up having this thing. Um, um, so then there's a unique isomorphism from H to E. Um, that commutes, and Vakil just invokes a ton of universal properties. Oh, and it's because by some other universal property, there's also a unique isomorphism from pre-sheaf, and sheafification induces that from H to epsilon. So, okay. Okay, I'm not super happy with this one. I'm not gonna lie, I'm not sure how much of this I'm actually picking up.
Okay. You mind going down 1 second?
Yeah.
Thank you.
I'm gonna kind of treat this section as I'm gonna go through it just to have seen it. There's gonna be some stuff that I just don't get.
Fair.
Um, the important thing I think is that we can come back and reference it.
Yeah.
Um, so yeah, because we're so close to kind of using sheaves in a meaningful way.
Mm-hmm.
Um, so okay, then in that case, that frees us to be a little bit more um, liberal with maybe not proving things, but just understanding them.
Yeah.
So the stock of the co-kernel is naturally isomorphic uh, to the co-kernel of the stock. Um, and I think that this just kind of follows.
Wait. So on the first one, the parentheses are outside the P?
Yeah.
Okay, yeah. Okay, that makes more sense now.
Um, so there we go. And then as a theorem, sheaves of abelian groups on a top space X form an abelian category. And so we've actually proved everything now. Since everything
Awesome.
has been shifted to stocks, and since stocks are abelian groups, we have an abelian category.
Awesome.
Um, so theorem exact sequences of sheaves can be checked at stalks. And y lemma let phi from F to G be a morphism of sheaves of abelian groups. Then the image sheaf M phi is the sheafification of M phi pre. And this goes off of the definition of image in an abelian category. And so basically this means that morphisms have a direct correspondence between their image sheaf and then image pre-sheaf. And then that means that within the image pre-sheaf, we can check exactness of phi at stalks. And so basically, like, this is saying that we just pass things through the sheafification functor as a way of checking exactness. This is completed by F alpha to G to beta to H is exact at G if only if for all X. FP by alpha P. So basically we have this thing, we use that to show that this statement, which is really sort of non-trivial, right? But basically it's, if we have exactness, we'll call this A dot, we'll call this AP dot. If A dot exact at G, then curve beta equals M alpha, but then this is equal to the sheafification of M alpha pre and then BP is in M alpha pre means that curve beta P is equal to M alpha P for all P. So AP bullet is exact. And then a similar process works for the other direction. And then that proves the theorem. So the thing that we didn't prove here was the lemma. Um, I don't really feel like proving that because that would require me to flip back to the section on Abelian categories. Um, and I just don't want to do that.
Mhm.
um, yeah. Um, theorem taking the stock of a sheaf of abelian groups is an exact functor. More precisely, if X is a top space and P and X, then FP, basically ab, abelian groups on X goes to ab by F goes to FP. Um, and so, okay, the thrust of this, like why we care about this, is that cohomology of sheaves is determined by right exact functors. Or sorry, by left exact functors and right derived functors of left exact
Mhm.
functors. And really, the way to think of right derived functors is all they're doing is measuring the failure of right exactness of a left exact functor. And
Right.
so we're about to prove, or maybe not prove, but state like 10 theorems about left exactness of things. And what we're really saying, anytime we say that a functor is left exact, it means that we can get a cohomology on this. And anytime that we can say that a functor is totally exact, it means that we have basically a trivial cohomology.
Okay.
So, like, taking the stock of a sheaf of abelian groups, well, the sheaf cohomology on stockification is trivial, right? Um,
Yeah.
like, that's what we're saying.
Mm.
Of course, one might argue that the right way to view cohomology is that cohomology is measuring failure of exactness, and so you care less about the structure of the cohomology than you do about the exactness, but I digress. Um, so yeah. Yeah. And so, right, like, okay, let me define this morphism a little bit better than I have. So if we have phi, well, really what we're saying is that we're sending a sheaf of abelian groups to abelian group at P, right? Like this is why it's a functor, and then the fact that it's an exact functor means that if we have a sequence of sheaves of abelian groups and we stockify all of them, um, so like if we have F going in to G going in to H with alpha and beta, well, we've already shown that if this is exact, then stockification is also exact. Um, but the fact that this is a functor is kind of what's interesting is that we're taking F down to FP, right? This is by phi. And then, we're taking G down to GP, but we're also taking alpha down to alpha P. And so we end up getting like this functorial thing going on. And all of that is accomplished by phi. And so then by this thing, which I'll also, I mean, this really is its own theorem. Really is its own theorem. Basically, we know that if this is an exact thing, then its exactness is preserved. More specifically, if we have 0 going in here, then we have 0 going in here, and if we go out to 0 here, then we go out to 0 here. And that happens by preserving the kernel of F. Does this all make sense? Like, is this all fitting together? I feel like I'm not really presenting this very well.
It's fitting.
Okay. That's what counts, I guess. So now we can check that the exponential exact sequence 2.4.9.1 is exact, and it's an exact sequence of abelian groups. So as an example, 0 in to the constant sheaf on Z into ox by 2 pi I into exponential to OX star into 1, where OX is analytic functions. This is invertible OX. Is an exact sequence of sheaves of abelian groups. And so, like we've already showed, I believe that this was exact. So we're sending functions from the constant sheaf to analytic functions. And then I just need to check something. So this is an additive group, and then ox is an additive group, and then ox star is a multiplicative group. So like if we call this alpha and we call this beta, then alpha of n is equal to 2 pi I n, and then beta of f is equal to e to the f. Um, Ox is a group because anything we add is going to pull out 2 pi I. Uh, and then it is a sequence of abelian groups. We've showed all of this stuff. And then exactness. Well, the kernel. Hmm. I need to use the restroom real quick. I'll be right back. All right. Sorry for the delay. Um, Garrett, you there?
Yeah, I'm back.
Yeah, sorry, my stomach is a little
Oh,
upset.
no problem.
Um, okay, yeah, so this is an exact sequence of sheaves of abelian groups. So the sheaves are defined on open subsets of the topological space, and by compatible germs of functions under addition. Um, and so, yeah, I don't know. I feel like this is pretty obvious. Do you want to go through this more? Because it is kind of our first down to earth example in a while, but
That's all right. I feel like I could work through this on my own time
okay.
and shoot you the next
Um,
any questions I have.
yeah. I'm a little split. Like these next three exercises, um, look pretty important. So I'm actually thinking about maybe we just end it here today, pick up at those three, because then that'll leave us an even amount of stuff to do next time.
Yeah, sounds good.
Okay, so then I'm gonna go ahead and stop the recording. Say this is good for today. We've done two whole sections basically.
Right.
Um, and recording, we will see you tomorrow. And then